Okay, my outstanding friends, before we even get started, we're looking at $5 billion to do this deep underground neutrino experiment to see if they can find neutrinos. Well, $5 billion, this is Fermilab. Now, here's the key. This is also Fermilab. They found these two particles, the black one and the white one, and the glowy one. This one has all the mass and is fixed. It doesn't get bigger or smaller. And this one has all the energy and has no mass. It just has a big energy field. I have shown these quite clearly that these are the neutrinos. They're looking for them for another $5 billion. Now, what does a neutrino, what do they say about neutrinos? Here's what they say about them right here. The muon neutrino is the black ball, which is that black ball, and the electron neutrino is the white shower. And they come from dipole neutrinos. All right, this event happened because of this. We shot laser light, which is this, straight forward into a venturi. A venturi is an accelerator. It's fully understood. It crushed the fields. Instead of hitting them head on, we made much more elegant design by crushing the fields sideways. You see it? It's and when it hit air, it was all bets are off, explosion big time, which is a subatomic nuclear explosion. I'll explain all this, I'm sure. And we separated the black from the white, creating the muon neutrinos in a sterile mode. Muon, sterile muon, exceptional. Electron showers, exceptional. Enormous amounts of energy, yes. No weight whatsoever, raw energy. And we did all that with a laser and a very inexpensive little venturi, tuned correctly, to completely eliminate the black and only allow the white to come through, which is what you want to harvest if you want electricity. That's raw electricity. We should be able to put that into a receiver device, some kind of a, almost like a solar panel, and suck it back in and use it. All right, again, this is it right there. That's the energy explosion. If we can pick it up on this side right here. So here we are right there. These different colors mean different transition metals, which are all these different metals basically that have different energy levels that they absorb. So if you had the correct number of layers of transition metals in the correct orientation of absorption of frequencies, you know how, anyway, the new absorption things they're using, these thin films, are very, very efficient. So you could harvest a lot of this white. And that's what you want. And you pump it down right into a device that would either collect it and store it, or just carry it around in a little lunchbox like this. Plug anything you want into it. Have all kind of regulation things inside of here to use anything, any USB devices and AC, DC, 50 cycle, 60 cycle, precise power, whatever you want. And a ton of it, because the output should be absolutely stunningly, enormously large. That is what they claim, and as far as I can see, that is the increase is stunning, stunning. Okay, my outstanding friends, another shocker du jour. We're talking about the DUNE experiment, Deep Underground Neutrino Experiment. And its cost has ballooned up to somewhere around $5 billion. Now they're looking for neutrinos. And let me explain to you what a neutrino is. Okay, my friends, if you've been following me, this won't be a shocker, but if you haven't, this certainly will be. This is a muon neutrino, and this is an electron neutrino. Normally they are tied together, called a Dirac neutrino. They can be separated, and the muon goes into what they call a sterile mode, where it's just a big black ball and goes by itself, and the electron neutrino part goes into a shower, a white shower. Well, we did this in experiments. These are the smallest particles they say that exist. Well, we did that with light, which also they say are basically the smallest particles that exist, if they even are particles. That's the thing, they don't even know. But I can show you they are particles. And I'll show you these in great detail, but this is the black muon, sterile by itself. They're all the same size. All the black ones are the same size. They're just a ball, and it weighs 0.0005854, something like that, atomic mass units. There's about 1,839 of them in one atomic mass unit, which is one proton. So instead of one proton being a ball like this that you smash into fragments of all kinds of things, but they're things. No, it's a ball like this of dipoles. It's dipole electron flood theory. Every one of these is a dipole. And I'll show you this, and well, I'll show it to you. Now, first of all, why is this so important? These are neutrinos. These are neutrinos that they're looking for. They claim they can't find them. This goes back to 2012, 2013, right in that area. And here it is, back in 2013, February 2013, Don Lincoln put this up about the particles that they found at Fermilab. And he says exactly the same thing. He says that the dark one is a fixed particle, never changes size. It's one size fits all, and it has a glowy edge around it. This is from his article. And the other particle is a glowy one. He's showing red, but we've seen them red, blue, and green. And they show those in those colors from Fermilab and from CERN. It seems to be those are the colors that you see. And even in the auroras, the same thing, the red, blue, and the green. Yellow sometimes. All right, so why is this so important? I just showed you neutrinos. That's what they're looking for, is neutrinos. We show them. We can even split them exactly like they do for Cherenkov radiation, only we're using light instead of heavy particles, which are huge things like this. We're using little particles like that. All right, which is light. Totally different situation. We don't have to deal with the big chunks. Here's what they have to deal with, is all this garbage. We're started with that. And we see these, absolutely. We see them spinning. We see them attached to the black particle. They don't, because they just see a big mess. And the dark particles, I don't know whether they see them or not. They appear to, because that's what Don Lincoln posted. Well, I'll show you his. All right, now these are X particles, are just chunks like this of protons or neutrons. We never even get close to that. We started down there with just the tiniest little particles, because there's nothing but dipoles, and 1,839 or so make up a proton. 1,840, which is a neutral number, make up a neutron. The neutron doesn't want any more electrons, and it doesn't want to share any. It says, I'm neutral. Don't come around me. I'm not going to give you any, and I won't take any of yours. This one says, I got an extra one. Anybody need an extra one? I will come over and attach to you. Or, in other words, it wants to share an electron to get neutral. So it add one or give us one up. Becomes a neutral number. And there is a whole variety of numbers in between neutral particles. They call isotopes, and there's thousands of isotopes in between every single atom. Each one of these, even hydrogen is not one. Hydrogen is 1,840 or so. Helium, I figured it out, I think it's around 7,300 and something instead of 4, which is 2 and 2 protons, 2 neutrons. And then it goes up, way up in here, you're up to hundreds of thousands, millions of particles. That's why all these half-lives can happen so fast, but it takes enzymes. Another issue. The root of everything is these, and that's the dipole flood theory. All right, so Don Lincoln shows those particles. These are the two particles. There they are, right there. I mean, you really can't miss it. And these are the smallest ones they can find. We started with light, so that's just the way it is. And these are the two particles, and we were able to separate them. Right there. Normally they're attached, and that's the strong nuclear, which is inside the nucleus, the strong nuclear force. When you rip those apart and you send the white off like this, you just created raw electricity. That's raw electricity, has no weight whatsoever and a ton of energy. And it exploded over here, created huge reverse electromotive force. And that's what they're all talking about. Oh, you can send energy backwards. Of course you can, it's just bouncing. Very simple stuff, and they're trying to make it all confusing now because this is it. And this was done 10 years ago or more. And just for full disclosure, I interacted with Don Lincoln, who is the author of this and of this article right here, asking about questions. And I asked, and I said, well, here's what we found, and can we talk? And that it did not go well whatsoever. And it still has, and it became extremely contentious, and it is till this very moment. And I think this $5 billion to Fermilab and so forth for their upgrades to find these neutrinos we found 10 years ago. As far as I'm concerned, these are the two neutrinos. This is also Don Lincoln. These are the Dirac neutrinos. Only he's saying this is matter, that's antimatter, that's backwards. That is the matter, that's the mass. The dark matter is the mass. We're made literally mostly of dark matter, surrounded by the glowy part, which has no mass at all. That's not matter, that's the matter. And the Majorna is well, I'll show you what the Majorna is, versus the true Dirac, which is half of a light particle, which is a gluon. All right, and here's how they go. And I'm going to show you their explanation and against mine. Here's what happens. They come in from here. Now, can you see that? I think you can. There's energy here, but it's not like a full photon. That's a full photon. It's sort of sideways here and getting stronger and stronger and stronger until it concusses. And at this point, this thing thinks it just concussed with a wall because we got a blowback of what's called reverse EMF, electromotive force, which is a backwards field. I'll show you that. So it starts to get energy, then it gets energy sideways, and then it just turns like that, a double dipole. All right, black and white is a dipole, and they're always straight up and down towards the Earth, up spin and down spin. And it's the muon wobble, which they can't explain. And as the leading one charges up, it flips, and this one comes in front and charges up, and I can show you that with the green. Here, they disassociate. They just go into what I would have to call fission, and they break apart. The black breaks apart from the white. It's quite easy to see. Can't miss it. Here's the Venturi. The blacks don't go with the white. Just the white. Exactly like they say. And neutrinos, these are the neutrinos, $5 billion to do what we already did 10 years ago. And, you know, I am not allowed to speak. I'm blocked at Fermilab, Don Lincoln, and again, you know, this did not go well whatsoever. I presented them, I said, look, we accelerated this light, and just like you guys are doing, they're doing acceleration, and they're hitting head on. So here's what they're doing. They're taking here's what we're doing, is going through a Venturi. So we have fields. There's fields around the things that they have. There's fields around them. So when they come, they sort of bounce off the fields. Normally, that's what happens. Every now and then, they'll hit one head on, but they won't even bang. They'll just smash apart into pieces. So instead of them fracturing into little thises and that's, all these things will go flying. Now, some chunks will be together, And these are the dangerous ones because they're very heavy duty. And some will be just in flashes of light. Light is not normally very dangerous unless it's so intense it burns you. All right, these, when they're big and they're like bigger particles, what they call X particles, they're dangerous because they're just so heavy. These here are like hand grenades. These little bitty ones, normally they won't hurt you unless there's so many of them at one time that your skin can't handle that intrusion of particles. It's like being out in this bright sunlight. You're going to get a little sunburn, that's all. However, the hand grenades are the X particles. And that's just a particle zoo, they call it. And they're right, it is, because they're just splashing things, huge things, when they should start down where we started, where light is. Okay, we are going to go see the banana girl in a moment, talking about neutrinos inside of bananas, because everything is made of neutrinos, and she's right. These are the neutrinos right here. Same thing they found at CERN and Fermilab. Only they see them again in a pile of literally debris. We see them manifesting themselves, accelerating, exploding at the venturi, and separating into the black and white particles, which are known as neutrinos. Not making anything up here. Muon and electron neutrinos together. They're tied together as Dirac. They smash here, here. Together, what you call a gluon, which is a gluon. Now, what else can we take away from this? All right, this is a really interesting shot. This is the two lasers going through the same venturi, one right above the other at the same time. And the green being much more powerful, and I believe it's literally moving faster. So it concusses here and with the disturbance of the red, and literally just pushes the red out of the way. And then it reconcusses out here. For what reason, I'm not certain why it didn't just continue here. But here that might have something to do with the camera, and I think it does, because you can see there's almost like a block missing here. But anyway, we can see the red normally would have been coming straight through here by itself and spreading this way, while the green is pushing it. But look at this. There's little bits of red up in here, which is confusing to me, to be perfectly honest with you. How that red got up in there. And what is it made of when it's up in there? Is it just... I know they're the same particle. No question in my mind whatsoever. A red and the green and then the blue, the same photons. It's the speed. And you can see the speed and the energy is enormous here compared to here. And it's pushing, I believe, faster and turning this spinning. Get out of the way and spin, and that just doesn't happen. No, they only spin this way, up and down spin. All right, this is a very, very unusual event. As far as I'm concerned, unless CERN can show me something like that. Now, remember this. I talked about reverse EMF. Let's talk about this, because this is very important to understand. All right, here's the whole thing. We're starting down here, and it was just a nice, clean wave. Everything's going fine. Everybody's getting out of the way. And then all of a sudden, it sensed the venturi and it started to accelerate, because a venturi is a natural accelerator. It's just a built-in accelerator. You're forcing all those fields, and it's slapping down here. The dark particles are literally slapping the white through that venturi, and the black itself cannot get through. So you have this concussion. You see back here? You see those waves? Those are reverse electromotive force. Normally they go the other direction. You see how they're normally going this way? Like swimming forward. Well, these are popping backwards. And there was a big thing, oh, now we can see energy going backwards. Of course, it's bouncing. You know, and I've been showing this 10 years. It's not like it's something new. So, and all of these particles in the air are, they're other molecules that are being excited. Their fields are being excited. Now what they are, they're electrons attached to something. Every electron's field will glow a little bit when it gets forced. And when it gets forced a lot, it glows a lot. And when it glows a lot, it gives off a lot of energy. These are only showing up here because of the pushback. That's the reverse EMF, and that's the subatomic. It's smaller than an atom because we're in the light range. Subatomic, nuclear, because only the nucleus exists in the subatomic realm. There's only nucleuses. Sub is smaller than the atom. So you're under the atom, which is under the nucleus. You're inside the nucleus. Subatomic nuclear explosion. It's just separated. The black separated from the white. If you can explain it in any other way, please do. Ask your physicists, teachers, and so forth, or if you're a physicist, or you want to be, or you're any kind of a scientist, you have to base your whole assumption of everything that you do in life on truth of what life is even made of. This is what life is made of, is light. We're made literally of light. These particles make up everything there is. They condense into, the first condense is into a particle, what's called a dipole electron, a black and a white. Then above that, the second one is where they turn into the photons, which is back to back like 2-bar magnets. Just like these. And this one's a down spin because the glowy is down, and this one's an up spin because the glowy is up. And the colors and these up, and this and that stuff is the flavors, they'll call it. Now we're going to see Fermilab's explanation of neutrinos that they want $5 billion to try to find, when I say we already got them. I say they got, and this goes back to 2013. Again, I was, Don and I did, we went back and forth until just recently. So I'm blocked, but anyway, this should not continue without looking at this information. This is very simple stuff. And the neutrinos make up everything there is, which is that right there. The black with the glowy around it, which is here. The black with the glowy around it. This is from Fermilab. That's exactly what Don Lincoln posted. And then he said this one has no mass to speak of, but it just has a field. And I agree with that. If you take two magnets and you push them together, when they repel, you hit like you're hitting a wall, but there is nothing there. There's nothing here. But it's almost, you can feel it, a good strong magnet. You almost, well, you can't really make them touch almost. The stronger the magnet, the harder. And I used to work with magnets when I was in the Army with nuclear missiles and radars. They used huge magnets. And usually there's no way you get them together. Me and this other guy, one time we ran each other with these huge magnets, and we just went flying across the room, bounced away from each other, and just for fun. I think we damaged the magnets too. But anyway, I can't be held accountable. That was long ago. Statute of limitations. So anyway, we go from here to acceleration to disintegration. And here's the green, like I said. Same flavors with the neutrino increases until you hit the photon stage. And there they are. And it's straight up and down, even though it's going sideways. In other words, it doesn't spin this way. It spins this way. And they do spin. So let's see what the neutrino girl has to say. All right, if you like physics or you know anybody that does, you should get them to see this, because this is just over-the-top stunning stuff. And here's what we show when they come back together as Higgs fields. That's when the white reattaches. And they actually, you can see this one, see it spinning right off here, and starts to create that field. All of them are doing that, it's just you can't really see it. There's so many spritzes coming off here at once. And this is where the black grabs right back onto the white at a certain distance from the Venturi, which is right about there. They start to no longer complete separation of white from the black. So we got to harvest that white right there if we're going to use that free energy. This is the cat's meow, and it's been meowing for a long time. The cat's getting old. All right, also, when I got no resolve from Fermilab, I took a course at University of Geneva, and I showed them all my pictures and all that stuff, and right away they said, oh, no, you can't do that. The same thing Fermilab said. But I was enrolled in the course there, particle physics, and so the professors said, they explained to me why you can't use CMOS because it damages CMOS, too much energy. I said, no. Well, I tried to be as gentle as I could be, and they were nice. They were very nice. I said, we are using light. You guys are using gigantic particles, so you're going to damage the atomic structure of the things that your huge things are hitting. Yes, that's true. But ours are CMOS, which is complementary metal oxide semiconductor silicates. They're a certain absorber of energy, but they absorb in the photon range, the particles of light. They don't absorb a big blob of matter like a machine gun. So I said, we're using light. So they went back and forth about it, and I kept showing them, and then the next thing I know, they didn't disagree. At the end, they were very nice about it. They said, well, we'll follow you. I said, well, can we work together? They said, no, we don't do that. We'll follow you on Facebook. Well, Facebook blew me off of there a long time ago, and it was just never productive anyway. It still isn't. So you're off the page if they don't let you publish, and they don't let me publish because I am a pseudoscientist. However, I noticed a couple of years later, or even I think it was like within a year or two, CMOS detector systems development for LHC. That's the CMOS. I told them, I said, that's what we're using. And they said, well, we can't use it because of the big particles. And I said, well, somehow you got to get it filtered down to just getting the light particles, or just use the light. Why don't they just use the light? Instead, they want to use the whole protons, which it doesn't make sense, because the proton, when it breaks apart into light. The more you can break it, the more light you get. The glory of the glow, the more electricity. And here it is, development of high voltage CMOS sensors. So these are high voltage, so they can, without exploding them. Large Hadron Collider upgrade took 3 years. CMS receive approval, massive detector. Green light for the U.S. funded portion of upgrade to CMS experiment at CERN. All of these things, they're looking for these particles I'm just showing you. These are the particles they're looking for right there, the neutrinos. All right, let's talk to the neutrino girl. All right, I have shown you that we already produced the dipole electron and the muon neutrinos, electron neutrinos, separated them, and brought them back together. And they come back together as Higgs fields. They think the Higgs fields separate and give off matter. No, the Higgs fields are when it comes back together, the black and the white, and they reform into a dipole electron or a photon or mass or whatever. So I think I've shown you, and this is $5 billion. $5 billion they want to do this. Since it's ballooned up, well, of course it is. They ask for a certain amount of money. They know it's never going to stay on the same plate. It's going to get... And now they want to dig underground. This project is just staggeringly... And there it is. There's what the particles they're looking for. And not only are they here today, They were here over 10 years ago. And I even, in my video, it was said, light is dark energy while traveling from the sun to the earth. That's right, because this is nothing more than particles of sunlight coming at us. It's dark energy. We don't see it. And dark energy is what we're built out of, basically, because dark energy is the only part that has a mass. And he says it. He says the only thing we can find that has the mass in these tiniest particles is this one. This one here has no mass and has just a field. This has all the energy. I agree with that 100%. And that was not me. That's from Fermilab. Now let's see what the Banana Girl has to say about their neutrinos and what they claim. And don't forget now, I showed you the neutrinos gaining their values. All right, they're getting glowier and glowier and glowier, and then just before they hit the photon stage, the flavors have been all used up. And I'm showing you light accelerating. There's no question it's acceleration. I mean, how could you possibly miss that? That's light accelerating. That is the reverse electromagnetic field. Enormous, enormous, enormous amount of reverberation. All right, this is, well, these are the Higgs fields being reformed back to being particles of light, actually, because they started out on the other side of the Venturi, looking very similar to that. Here's when they just first start like this. This is what it is. That's what light is. You don't see it. The only reason you can see this one is because it's starting to accelerate. And this is a very typical wave. There's no light out here at all. I mean, you can see it's black, but that's just a cutoff. But there is no light out there. The light will just continue to keep pulsating from that red laser. This is the beginning of the light wave. And it's a wave because the particle the little particle is inside here. And it has a big, big field around it. The black and the white particles. They have a big field around it, and it's got to go through everybody else's field. Get out of the way, get out of the way. So they glow a little bit. But this one is the one that really is pushing. All right, so now what does it do after that? It hits for the Venturi. Like our rocket ship. Right into the Venturi, and that's the only one. And they are everywhere, they're everywhere, they're everywhere, and they're being pushed back against, so now we're seeing them inside this ball of explosion. And that, my friends, is one hell of a luminous explosion. And luminosity means increased energy. Increased energy from what we started with, which is almost zero, to this here is literally staggering a number of times. I mean, I can't imagine how, if it's, and they also claim it's hundreds of times. If you can do this, if you can break the white away from the black, you got at least hundreds of times more energy. And I would say that's every reason to believe that. And what we got to do is harvest it right there. When I say, oh, we got to do it, it's not that easy, but it's not hard, I don't think. And this would be the solution to virtually all our problems, but it's kind of late now. All right, so you know that they're even trying to upgrade even more to be able to use heavy ion detectors using the CMOS. The CMOS is the only way to be able to see without you putting in the interferer. You know what? I got to tell you something. You see this? They're still, as of 2023, they're still adding more detectors trying to get the next generation of CMOS, which is a complementary metal oxide semiconductor, pixel sensors, in a 65 nanometer technology with higher radiation tolerances, for the 2030s, to see these things that they found in 2012 and just can't accept. Development of high voltage CMOS sensors, and this, you know, and again, I mentioned this to them, and I talked to Don Lincoln about it too, and he, oh, no, and he just shut me out. At least they listened to me over there at University of Geneva, and they're doing it. And the only way you can see this event without interfering with it, adding energy or taking energy out, is to use the CMOS, where it just sits back here and absorbs what it shoots out. Now, for them, they're shooting out chunks like this. It destroyed the CMOS. For us, it's shooting out light particles, that's what the CMOS is designed for. We can see it, they can't. And they're doing all this huge amounts of money, and they're looking for these particles, the same neutrinos. Okay, this is right from Fermilab. This is a Fermilab production. You see their little logo over there, like our Caesar. All right, and this is with Kirsty Duffy. She's the neutrino girl. And it's called Even Bananas, and everything's made out of neutrinos, and I agree with that. So here she goes.
Welcome to the second episode of Even Bananas. We're back to focus on our favorite fundamental friends, the neutrinos.
Fundamental.
There's a lot more to neutrinos than Wolfgang Pauli ever imagined when he first suggested they existed back in 1930. And before we dive into the details, I thought it would probably help to give you an overview of everything we've learned about neutrinos since then.
All right, she's going to give us an overview of everything that they believe about neutrinos. She said that we've learned, well, that they believe, and we'll see what they believe.
And I bet you're wondering why this show is even called Even Bananas. We'll get to that as well. So today, I'm going to do possibly the hardest thing I've ever done in physics, explain neutrinos in under 60 seconds. All
right, timer on, please. Okay. Neutrinos are fundamental particles that can't be broken down into smaller bits. Now I'm going to slow her down because she's going to be rattling on here like crazy. I'm going to go playback speed 75%. How about that? Now, you get ready for this because she's going to be moving like a rocket ship. I'm going to be stopping her here and there. You have seen my evidence of what neutrinos are, and they are exactly what CERN and Fermilab and everybody else says they are. Now let's see what they say, because let's see what they have to say. All right, you ready? Okay, here goes the timer. She's on 3/4 speed.
Please? Okay. Neutrinos are fundamental particles that can't be broken down into smaller pieces.
All right, they're fundamental. I agree with that 100%. I showed you those fundamental pieces, the black ones and the white ones. The white one has all the energy and no mass. The black one has all the mass. Now she's going to show them on this chart.
They're
here.
the second most abundant particle in the universe.
The second most abundant. They're made of everything's made of the white and the black. Now let's see what she says. I'm going to go back a second, make sure we don't miss anything.
Second most abundant particle in the universe, second only to photons.
Photons are made of two sets of neutrinos, the direct neutrinos, two sets back to back. I showed you. Now she's saying they're the second most abundant in the universe, second only to photon particles, which are particles of light. Yes, particles of light make up everything. And the neutrinos are pieces of the photons. That's what neutrinos are. I've shown you that very carefully, very clearly.
Particles of light. Almost every time atomic nuclei come together or break apart, neutrinos are produced.
Exactly. This is exactly what she's saying. The nucleus is like this. When they break apart, neutrinos take off. Yes, absolutely. I agree with that 100%. And light is made out of subatomic particles. They're parts of the atom's nucleus, but they're sub-parts. They're little bitty parts. All right, so here we go. Let's go back. I don't want to miss. And I don't want to miss a thing. Almost every time atomic nuclei come together, which is smashing them, she means, with these colliders, and they break apart, neutrinos are produced. Yeah, there's no question about that.
Come together or break apart, neutrinos are produced. And that means that almost everything produces neutrinos.
Exactly. Everything is made of neutrinos as well. Everything produces neutrinos, including stars, the Earth, the people, were all made of neutrinos, yes.
Including stars, the Earth, people, and yes, even bananas. Like delicious Neapolitan ice cream, neutrinos come in 3 flavors.
All right, here's where I'm going to comment. Let's see what she has to say. She's saying neutrinos come in 3 flavors. She's going to be talking about the electron, the tau, and muon, and so forth. Well, let's listen.
Electron, muon, and tau neutrino.
All right, so she's saying there's 3. Tau is just a different variation of the muon and the electron neutrino. It's in a different, you know how I showed you some of them are looking like this and some of them like that, and then you show the actual photons. The tau is one of these flavors. All right, so this, and the electron and the muon are extremely obvious. Those are the black and the white.
This is where it gets weird. Neutrinos can change types as they travel. It's called oscillation. It's something we didn't expect and still...
All right, let's just look at what I showed. She's talking about oscillation now. That's where they were spinning like this. And they may not have suspected them, but we can show them very clearly. All right, the oscillation is, this shows the spin, but I can show you much better. Let me show you correctly, hold on. All right, this is light coming through the venturi, and every one of these is a photon. And when they spin and they start to come together and bang each other's fields, they glow a little bit. As they came apart and they're sort of finding their own way apart from each other, they just get diminished in light. But after the venturi, they're trying to find their way to separate, and they're starting to separate enough where the glow is diminishing. But this is light, and that's spinning. It's not flapping like this. So here's another shot of this, and you can see how this is bundled up. They're too close together, so they just, one of them's glowing. This little region is glowing. You see. And when they impinge on each other's fields, same thing down here a little bit here. When they're sort of apart from each other, there's just no banging into them. You see, that one just trailed right off into nothing because it's not banging into anybody else's field. Now this shows, I showed you the spinning particles. The blue spins much too fast to really make much of it. But this is looking straight down and seeing the pattern on the wall from the spinning particle. So we're spinning through this slit, and I'm pretty sure it's a single slit, but it doesn't matter. It could be a multiple split, but they spin like this, the particles. The key to it is you have to have a venturi. You've got to have a venturi coming in here. You can't just have a flat plate. The flat plate looks like there's waves flapping like this. It's not. It's the spinning light. You see it spinning high up here? That's a drill bit, a literal drill bit going in of light spinning. And I showed you the light spinning, and here is how it spins. And the blue and the green and the red, same thing. It comes down and spins like this, over this way, and bang here, and then down and under over. That's a drill bit. And it's a right-hand spin. That's the right-hand rule. And in other words, if you're going that right hand, if you're going this direction with your thumb, it means the spin goes this direction, which it does. So that's a right-hand spin. Follows the right-hand rule. I can live with that. Now, normally they see them like this, and they say that's a wave. Well, it looks like a wave, but it's actually a spinning particle. Now, when they're right down this tight like this, you're down where blue is. When you're out here somewhere, you're in the green, and when you're way out here, like you're in the red. It's just how fast it is and how concussive that particle is when it hits something. When it's blue, it really whacks the stuff. When it's green, it's pretty strong. When it's red, no. It's in the very low end of the spectrum. It's way down here. When you're up here, once you hit the ultraviolet catastrophe, that means the spin is so fast that the white takes off, never comes back. and all you have left is the black. Because this is black and white spinning through here. And at the ultraviolet catastrophe, it's gone, and now all you got is X-rays and gamma rays, and those will kill you because it's just black. There's no more real energy given off. All right, it's luminous, 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 and then right down to zero. That's the ultraviolet catastrophe. So everything I'm showing you proves exactly what I'm saying about dipole electron flood theory. There's no, I can't find anything that violates my theory. Nothing. I can see particles going faster than other particles. One pushing the one out of the way, the green, yes. I can see the blue spinning very, very fast. Coming in here and spinning and then slowing down, showing that it is a photon with two little dots instead of one. Over here you can't even tell. The blue, you know, through glass, it made a very interesting pattern. It looked like a spaceship, really very interesting. Hold on, I'll show you that. Check that out. You see that wave coming through the glass? That's the most impact right there, but that's the feel that it makes in the glass. Can you imagine? I'm telling you, the amount of time Rod put into this, I just can't even imagine. I got to be honest with you. I was just stunned at his dedication to doing this. But that was 12 years ago or more. So at a certain point, you know, I hope he's okay. I haven't heard from Rod in a very long time now. But this was his, virtually all of this, well, almost all of it was his pictures. And without his original input, nobody would ever even consider to do this. And when I saw, I think this was the one I saw. When I saw that, I said, whoa, this guy's got dipole electron flood theory in a picture. In a picture, there's no question what it's doing. Acceleration of that light particle and explosion of the dipole. And then I can't remember. He was flooding the internet with pictures, and when I saw these and I started, he was very, very forthcoming, and I would ask him about, well, can you do this? Can you try that? And apparently he just put in tons of time on it, and we found the same particles as they did at Fermilab, and this should be looked into. This deep underground experiment for $5 billion. That's not right. If at least look at what I'm showing. If it doesn't come to pass as being correct, well, that's fine. Sometimes I'm wrong. You know, sometimes. But he's showing the same particles we're showing. And he even says, when you look at these things, the field gets stronger. Well, that's because he's putting light into it. It's fighting back. So he says that's the observer effect. You look into this, it gets stronger. No, it doesn't. Just by looking into it has nothing. Your eyeballs do not affect that. When you push light into it or you suck energy out of it to sample it, you have disturbed it. That's the observer effect, absolutely. But they always thought just because you're looking at it. I'm not kidding you. They used to make the people leave the room because they thought just by them looking at it, they were disturbing the effect. No, it's because you push light into it and it fights back. Is exactly what Don Lincoln says. I can't read it on here, but he did say that the stronger you look at it, the bigger the field gets. I believe that was his statement. He also states that there's a quantum foam and that there's no empty space. There's no empty space. Quantum foam dictates the fact that there's nothing but particles in interstellar space. It's exactly what he says. Not making that up. It's called a quantum foam. It's like the fuzz on the head of a root beer. He says it just flicks on and off all the time. That's because these particles, which are light, are moving through bang, boom, bing, boom, 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 boom. And I was showing that on the tether experiment as well. You could see them all flickering in the background because the light is hitting them. Anytime light hits something, it makes a little flick. And it also slows that light down, so Webb telescope is not doing the job they said it would do. All right, so I showed you the oscillation. They charge up as they go forward, and then they flip, and they flip, and they flip. It's called a muon, or wobble. So this, I'm coming back here. She says they can't explain these things. You got the muon, the tau neutrino. Tau is the middle of the road neutrino. It's a flavor.
Neutrinos can change types as they travel. It's called oscillation. It's something we didn't expect and still can't fully explain.
Yes, and as you ask me...
Theory says that neutrinos don't have mass, but they...
Whoa, theory says neutrinos don't have mass, but they do. Yes, they do. The theory is wrong. Excellent point.
Do. Unfortunately, it's so small we haven't been able to measure it, which is great.
Actually, it's 0.000585 atomic mass units, approximately, and 1,839 of them make one proton.
Finally, neutrinos are pretty antisocial. They don't like to interact with other matter, which
Okay, now we come to a point of neutrinos being antisocial. Yes, the white ones say, get away from me. And they create these, what they call interference patterns. They're repulsion patterns. However, the black ones are extremely social. They don't mind being all right around their own self. They don't push each other apart. In my model, they don't push anything apart. They collect in the center of everything, and they're surrounded by the white particles. The black ones are extremely social. They go both ways. The black ones can come in and they all congregate together, and the white ones come in and they hug them all together in one big ball. So everything we see is coated with glowy little particles that want to be on top of the black particles. But if we dove inside, we would find the blackness in the center. So we never see it. That's why we don't even know where black matter is, dark matter. They say almost the whole universe is made of dark matter, but we don't even know where it is. Well, we are part of that. We are part of dark matter. So let's come back here. We don't want to miss anything Neutrino Girl says. She's saying, unfortunately, it's so small we haven't been able to measure it. Well, yes and no. It's pretty small.
Finally, neutrinos are pretty antisocial. They don't like to interact with other matter, which obviously makes them hard to study and means we have to build huge detectors to be able to do it.
Wrong. You need to make small detectors to be able to do it using CMOS, as I mentioned to University of Geneva, and CERN is now using CMOS, and they have shrunk everything they did down to a little cylinder now to squirt out these neutrinos. But they're trying to do it with, it's called phaser or something. I'm not going to explain what they're doing, but they're coming down to the photon phase, into photon colliders. They were always proton, huge particle colliders. Now they're coming down into the photon phase. They realize that is the future of physics, is obviously working with the photon, the smallest particles we can get to. Why start with a big ball of, why don't they just start with a mountain? Why don't they start with the moon and try to whittle that down until they figure the smallest part of that?
So why do we even bother? Well, neutrinos might explain why the universe exists and why there's no antimatter around.
This antimatter stuff, it's a dipole electron. There's a positive and a negative. You call them anything you want. The matter is the black part. The white part is the energy. It's not matter, so I guess you call it antimatter if you want, but it's the glowy energy. All right, so now she thinks she's explained it.
So if we want to understand the universe, we have to understand neutrinos.
Exactly.
I did it.
Yeah, all right, banana girl. Okay, if this is true what they say, by doing this and creating electron showers, we should be able to increase the amount of energy exponentially. And that is what they say. This is the physics of electron showers. Creating these, first they want to use protons, then decay those into hadrons and yada, yada, yada. And then they want to get down to where we started with the neutrinos. And they interact and give off a few 100 billion electron volts to trillions of electron volts. That is an enormous increase in energy. And I'll show you the graph that they show. All right, this is what they call base tracks of muons versus electron neutrinos. And they're vastly different. See, muons are not very separable by energy. In other words, they don't push each other apart much. The max energy of muons and electrons are vastly different. Electrons are absolutely unbelievably energetic. And I'll show you what happens when you separate them from the muons right through the roof. All right, this is the actual event of this. Now watch what happens. We're coming in from here very low energy, almost no energy at all, until it starts to accelerate, and then it gets extremely high energy, and at the Venturi, it goes right through the roof. That is just raw energy. So don't forget, we're getting smaller, and then it's getting glowier and glowier. That means the electron showers are getting big, and then they explode at the Venturi. Now the muons can't get through. They're backed up right there. They can't get through. And here's exactly what they say in the visual right here. This is coming in, this is the number of particles in the shower, and this is energy. U means energy. Now the number is coming bigger and bigger and bigger and bigger, and right at the Venturi, it goes through the roof. So this shows you how many showers the base tracks are. In other words, how many particles. And it comes in, not accelerated, and then they start smashing into everything. And they start ripping particles apart. And then, right at the Venturi, right up through the roof. That's not my graph. That is the graph from, I believe it's from CERN, it might be from Fermilab. They work pretty collaboratively. And they have both the same ideas, which in my opinion are not correct. And I think we can do this in a handheld device using those little lasers. And if we can increase the energy from here up to here, I mean, that's just staggering amount of increase. And in our case, it's for free, because we really didn't do anything. All we did was shine the light, which is the laser, through a Venturi. It only takes, let's say, 5 watts to run that little laser, and you should be able to get at least 1,000. That's 200 times more energy than you started with. And that's what the graph shows. That's not my graph, that's their graph. It's way up here. This is energy. U means energy. What does energy mean? Energy means electricity, basically, in this case. And it's both types of electricity. It's electricity in use, which means you're using it right now, kinetic energy. It's doing a job right now. It's being consumed and used up as it's being created. That's one type of energy that we're making. And in addition to that, we're making potential energy where you can charge up batteries and anything else. All right, you want to make potential energy and charge and store it somewhere, that's fine. But you can also carry it around in a handbag, like they used to in the ancient Sumerian days. You plug anything you want. And this should give you more than enough energy to do virtually anything you want to do. You know, it'd have to be engineered right, and it'd have to be this is a little engineering, very minor stuff. And it depends on how much energy you need. You might need a big one. You might need a small one. Doesn't matter. It's going to be portable. You don't have to plug into anything. It does its own job inside here. Then you run it through a couple of bridge rectifiers and so forth into some capacitors and whatever you need to store just enough to do what you need to do, and then feed it off or have a battery in there. You do whatever you want with it. Put it in a car, put a couple of them in a car, you drive, never have to stop. And you never have to pay for any of that stuff either. No energy expense and no damage to the environment. None, zero. It has no emissions, no expansion to the atmosphere, nothing. That white is just literally almost not there, but it's just got all the energy. It's just hard to explain. Very, very hard to explain. But I can see it, and you can see it too. If you don't see energy there, that is energy on steroids. That particle is coming through here with not much energy, and that's what they're trying to get at the super colliders. That's it right there. The black backs off, the white squirts through. And it's just got to do with the tune of the Venturi and the design of the Venturi. So don't forget, here's where we started with this DUNE project for another $5 billion to look for these neutrinos. I think I just showed them to you. I think somebody at the government should be interested in this. They're firing all kinds of people for doing whatever they do, and they're trying to get rid of waste. I'm good with that. We don't want ballooned waste. And really, this has denied us from looking into this for 10 years. And it's because, well, it's because of whatever it's because of. I'm not going to make any accusations here, but it seems to be that anytime you want to interfere with somebody's budget, you got issues, and especially when they're in a position of power where you can't speak. And that's my situation. I am not in a position of power, and I cannot speak.